So first and foremost, I'm just going to show the destinations, the distances, the elevations, and I'm going to show the elevations of the land masses that we are looking at. First destination is here, just at this point here. Okay, as I pointed out before again, just going to have a wee scroll through here. Different day, Ailsa Rock clearly visible. The elevation of that point and the height of the camera on the Google mapping van is not going to be that much different. You know, we were here, so the tripod had an elevation of 2 feet. So that's the first destination. Here, so we're seeing here the bottom 1.2 meters or 3.9 feet. So we'll add the 2 feet of the height of the tripod and the camera, so 6 feet. There we are, 62.66 this time, so it's kilometres, so 38.9 miles. So you can see here where we are. Get it?
Yeah.
Now, there is the rock. Now the important thing to notice here is this reflection here, people. Okay? Hugely significant, hugely important. You're seeing the reflection of the rock because the water is continuing all the way, but because of this band, the optical effect that we don't have an exacting science for here, because our vision is limited and the sky is being reflected on the water, right? Same as the rock is being reflected on the water. So we can see up to this point, which would be our horizon, and then beyond that we're having serious problems. I mean, you can see other objects here in this band, right? But the important thing is the contours of the rock and the reflection on the bottom of it. Now, that rock is only 1,100 feet in height, so the calculation for that distance was 800 odd feet. So really you should be seeing about that much. The obstruction should be away up here, right? And that is beyond. So you're not looking beyond a curve where the rock is being refracted up into your visual range, horizontal, perfect for you, and displaying a reflection. Okay, solids display reflections. Mirages and imaginary invisible stuffs do not. So the huge significant aspect to that is the reflection that you're seeing on the water that's leading all the way up to it. Alright? So that's the first observation from Largs to Ailsa Rock.
Right now I think we must be a bit even more than that, actually.
The second destination is here. So this is where we parked. and we walked down onto the beach here. So we're looking here at the rock again, and also the peninsula here that you're going to see in the observations, which reaches out to Stranraer. So that furthest point that we're seeing there is 75.5 kilometres, miles 46.9. So we're seeing a generous 8 feet to this, although it's no. Right, there we go. We're at 8 feet, 46.9, 1200 feet curvature. Right. And I'm going to come across to the landmass here, and I'm just going to randomly dot it. So that first one is saying it's a height of 125 feet, 317 feet, 682, 777, 500, 400, 337, 605, 703, 480, 700, 770, 700 again. Right, there's a maximum point there of 1455 feet. So the curvature is 1200, it should be missing, so we should really be seeing the tip of this highest point here, and that is about all. Okay, so huge distances. I think I've covered the location and the distance and the elevations, so let's now go to the footage. So this is the second destination. You can see how low down we are here, right? But I was generous and gave it 8 feet. So you can see the rock here, but this observation is not the one I'm wanting people to focus on. It's when we cut across to the peninsula. Again, you can see the reflection here. Here's the important parts as well. So remember the elevations I showed of this whole area up to this far point, and the highest being 1400 feet, which is all you should see. I mean, here you're seeing the wind farms. So if I just go back to before we scan it. You can see the landmass here, stretching all the way across. Remember, you shouldn't be seeing any of this. Highest point here somewhere or here, but we're saying 1400 feet is all you should see. You shouldn't be seeing any of this. Absolutely none of it. Okay, it should be gone. Right. Now, I don't want to keep going over and over on it, people. As I said, you know, first and foremost, see this stuff here. This substance that's abundant on Earth that we know and that we can test its physical properties and its behaviours, and everybody can do so. We know that from this landmass to that landmass, this substance in between here is at the same elevation. It levels out. The substance does not have the capabilities to hold itself and display convexity upon its surface. It is level from here to here, from here to here, and from here to any other landmass that's way beyond. The body of water is level. That is a fact, fundamental fact. The optics are always going to be playing a role It is something that we did not have an exacting science for, but what you can, take from this is that none of this should be visible. The rock from Largs, you should only be able to see the top 150 feet of. When you can see the whole thing and you can see it reflecting in the water underneath it. There is no excuses that anybody can come up with, right? No amount of equations and wishful thinking is ever going to change the fact that the substance from there to there is level, and that we are actually seeing things that are actually there. And the tens of thousands of people who live all along this coastal route see these things just about every single day. And in the right conditions, they can see all the way across the island. So let's have a wee look at Google Maps. So we're talking about here. We'll go to the closest point. Just about 100 kilometres, right? So nobody should be seeing any of that. That should be way gone on your imaginary ball. All this blue stuff here, I suggest that you understand this substance that's here, this abundant substance that from each point to other point of landmass is level from one point to the other. That's its behaviour. And you are so tiny in comparison to these vast distances. You are being obscured by all sorts of atmospheric conditions and limited perspective.
Here's an interesting video I saw online regarding a full day time lapse. Now, this is quite extraordinary, actually. This is from skunkbayweather.com, September 7th, 2012. Notice the buildings and the shoreline here over on the left. Keep your eye on that. Just watch that, and the mountain in the background. Everything's pretty cool. You can see pretty much everything there, but as the day progresses, and we are now at 9:30 a.m. and it's 59 degrees, 60 degrees, it's getting warmer, the temperature is changing, we start to see some miraging take place, right? It starts to distort things a little bit. Ooh, look at that. The water seems like it's getting higher, and we're losing buildings, and we're losing the beach. Here it is now, noon. 63 degrees and climbing. Uh-oh. There it goes. Oh, there it is again. Oh, it's all miraged. Huh. It's all distorted. Sometimes you see it, sometimes you don't. The default is to see it, though. And that's the point. The default is minus distorting atmospheric conditions. You would be able to see everything clearly. But due to different temperature variations and density in the atmosphere and whatnot, sometimes you can see the whole shoreline and the buildings, sometimes you can't. But the magic trick is not in being able to see it, it's what is taking place that obscures your ability to do so. Look at this. And the mountains in the background shrink and expand and everything too. I would suggest that you hit pause on this video and rewind and watch that back and forth a few times. Look at the comparison right here, just in these two images right here. The one on the right at 5:44 p.m., 63.5 degrees Fahrenheit. Can't really see anything on the left shoreline there. And on the left at 9:43 a.m., when it was 59.5 degrees Fahrenheit, we can see the shoreline, we can see buildings, trees, all kinds of stuff. So, I mean, either this lake is, filling up and draining so that the water level is higher or lower, or it's due to atmospheric lensing and distortions, refraction, and all that good stuff, causing us to not be able to see at a certain time.
Now I'm going to stand back and just show you where my camera's at. This is where I normally film from. There's this little path, and there's the boardwalk that they put out here. again, you know, I'm saying that the water's actually even up higher, you know, and you see the mirroring going on underneath that rack. Of course, it's distorted. It looks like a mirage, but there's no magical force pulling that up. You can see birds land on the damn thing, for crying out loud. As I zoom back, you know, you can see the layers of clouds. And there's always that little gray spot in there that I like to call the gray area, because that's where I think that convergence is at. And again, look at the mirroring that occurs on this. Okay, see the mirroring of those bird racks? And what's cool is seeing the birds. The birds give it away. It shows you that they can be in mid-flight and they'll disappear underneath that mirroring area. And that's why I say that's what cuts off buildings and objects, is that mirroring effect that occurs. It's an illusion. And there's that Bill Watts rack right there. Zoom in on it and see how it's being affected there. Hopefully we can catch one of these birds or something. Okay, here we go. Okay, I'm back down here at Bayport again. There's the deck. Here's my camera. And look how much farther in the water is. Okay, I'm just going to let it sit there. Show you. And what I'm curious of is if I can find that other bird rack that I tried to find this morning. And what I'm curious of is if I can find that other bird rack that I tried to find this morning. No, shit, there's the bird rack. Look at that. And then there's one to the right of this one too. Look at that. That's even further back. Holy crap. There's the sign. Huh? So tell me, how am I seeing that? I couldn't see it this morning because of the light refraction, but here I can see it now. It even looks like a boat or a canoe or something sitting out there. He's just doing some flats fishing or something. just sitting in the water without all that reflection. See if I can find this other. The shrimp boat coming in.
Here's a good question. How high does one have to ascend in height in order to actually see curvature? Like, there's got to be a mathematical formula for that. I mean, this is a good question. So if one's line of sight maintains focus at the horizon at all times, and we ascend and climb straight up, higher and higher and higher, how many miles up is it before we start seeing the actual curvature of the Earth and into deep space, if you will? I mean, this should be, from my understanding, a mathematical constant, probably an exponentiating mathematical constant at that. And yet again, if the Earth is spherical, and help me understand this, shouldn't there be yet another general mathematical constant as to how far away the horizon will be? So if you're standing at sea level for, say, a 6-foot tall person, it's not me, 6-foot tall person standing at the sea level, should the horizon not be, generally speaking, a set distance away? If your line of sight is on the horizon at the whole time and the Earth is curved, that horizon line should be, in general, generally speaking, a set distance away. That should be a mathematical constant. That seems very reasonable to me. The first one is from YouTuber Jenna Freda, and it's an incredible video of Jenna zooming her camera across a lake at a distance of over 30 miles. And as you can clearly see right here, you can see almost the entirety of the city with just a bit of the street obscured from view. And then she shows a shot at the end of the video of the city skyline and then a screenshot from her video. And they look pretty damn close. Almost identical. And then ODD shows another video of an independent balloon launch using a camera with no fisheye lens, so there's no distortion in the lens. And this balloon reaches elevations of over 121,000 feet, which is nearly 23 miles. And as we can clearly see, not an ounce of curvature is to be found. We see neither curvature left to right, nor descending away from us. We see none at all. You know, it would be really great to get responses about this singular question of curvature that doesn't rely on ad hominem attacks or misdirections or calling people stupid or anything of the like. I would just love to focus on this one question. Can we measure curvature? Seems pretty simple. I don't want to hear about globe heads and flat tards. I don't want to hear about how dropping a mic on TV somehow proves gravity, or how the southern star rotations don't work on a flat earth model, bro. I don't want to hear about how the sun can't possibly be 93 million miles away, or dude, the lunar eclipses don't work on a flat earth, idiot. I don't want to hear about how there are no satellites, or how Google Earth proves the sphere, or how Google Earth proves the flat earth, or what about the Coriolis effect, or how Eric Dubé is a secret agent working for the CIA infiltrating the truth community, or how Aristophanes proved this shit a few thousand years ago, dude. I don't want to talk about any of that. I want to focus on one question. Does the Earth below our feet have the curvature that we're told it has? Because if it doesn't, then the entirety of the science attributed to it falls flat, if you will.